lecture of the Symmetries course. And Uwe, whenever you're ready, you can get started.
Yeah. Thank you, Marielle. Thanks for coming after a lot of talks this week, so I appreciate it. And all right, so forgive me for cheating a little bit by not writing down, having written down already something we discussed yesterday. So we started with an ink invariant chain and then defined what I called an equivariant Hilbert series. It's a formal power series in two variables. And I recall the definition. Basically, for each n, you have a quotient ring. In each degree, it's a finite dimensional vector space. Take its dimension and then multiply. Keep track of the degree and the stage in the chain you are by multiplying by suitable powers of the variables. And we have seen that's always a rational function. We looked at some examples, and then we started discussing how to compute this, actually. And I want to illustrate this in the case, or discuss this in the case where all the ideals in a chain are monomial ideals. One can reduce the general case to this situation, but I don't want to talk about this. Once we are in the monomial case, the problem of determining this Hilbert series is really a combinatorial problem. And so we started by discussing languages, which are, well, we have a finite alphabet, and then we encode, words are just strings of letters in the alphabet. And we wanted to use this to encode monomials in our favorite polynomial rings by words. And as alphabet, so we have always our polynomial ring with C row variables. And then for this ring, we choose as alphabet sigma, C letters, zeta 1 up to zeta C, and tau, so the zeta i's were replaced by xi1s in the encoding and the tau by a shift operator, and then applied. And then we had seen, given any filtration of chain of monomial ideals, ink invariant, this encoding induces a bijection for a suitable regular language, L, where you take sort of sub-languages, the words in the sub-language Ln are in one-to-one correspondence to the monomial I sub n for each n. And the sub-language L sub n just consists of the words of the language L in which each letter tau, in which the letter tau occurs just n times. We just keep track of the repetitions or the number of occurrences of tau. And yesterday it was pointed out, well, I mean, this map is, I mean, as given, this is certainly not bijective, because if you have a substring zeta 1, zeta 2, it produces the same monomial as if you switch the order zeta 2, zeta 1. And I said, well, you just order these. And so let's, I said this can be done. So let's review this. If you just look for words in the alphabet, zeta 1 up to zeta C, but you allow only words where any substring of the form zeta I, zeta j satisfies that I is at most j. That means you keep the order, you fix the order of your indices of the zetas. I said yesterday this is a regular language, and well, sorry. This is the proof, because we had seen if you take one letter and pass to the star, that's a regular language. So this is true for any of these parts. And if you concatenate, you still get a regular language by definition. All right. So, but for now, the important part is we replace counting monomials in these ideals I sub n by counting words in Ln. And to do this and connect it to our goal, we need a suitable definition of weights on our words. And so let me formally introduce this. Namely, we say a weight function on the formal language L is a map, let's call it V, from the language again into some set of monomials in a polynomial ring. So let's say now we call the monomials T1 up to some Tk, and then we take monomials, and we have two requirements on the map. First of all, the empty word should have value weight 1. And if I concatenate any two words, W1 and W2, where the weight of it should be the product of the weights of this individual parts, right? V of W1 and V of W2 are monomials, we can multiply them. And so if you, I could say this more abstractly, but this is no new information, but just maybe for context. So that's the same as we're saying that this map V is a monoid homomorphism. All right. Let's see how we can have such an example if we use the encoding we discussed. So let's stick to the case with our alphabet sigma consists of tau, zeta 1 up to zeta c. And then we want to define and weight, and we do this actually from sigma star into, and now we take just two monomials. Monomials in a ring of two variables, S and T, where we map a word onto, well, it's a monomial in two variables, S to the n times T to the power j. And now I have to say what is n and what is j. And well, n is the number of occurrences of the letter tau in W, and J is the number of zeta letters in W. And if you remember our encoding, the zeta letters were replaced by axes, by variables. And so this is the same as the degree of the monomial corresponding to W under our encoding map mu. And then I think it's easy to see, and I encourage you to make sure that this is a weight function. Okay. Now, why does this help us? This is because of the following combinatorial result, which is due to Honkala, but you could also find it, for example, in the book in Stanley's enumerative geometry. And this says, the result says the following: whenever you have a regular language L, and a weight function V, then you can use these weights. Well, here are the other weights. They are monomials in a polynomial in k variables. If you sum over these, you get a formal power series in k variables. And so let's consider, and this one should look at. So this is a formal power series in T1 up to Tk. And that's, by definition, the sum over all words W in lambda, and then you sum over the weights of W. And the result is, this is always a rational function. Okay. So that's good, right? We want to determine a rational function. That seems we are on a good path. And indeed, we can connect this now to our goal. And this is actually, this has been made explicit in the paper by Krohn, Lakin, and Snowden I mentioned yesterday. Namely, if L is the regular language to our filtration I with components In, then the following formal power series in two variables, where you take sum n at least 0, j at least 0, and then you sum over, and now we sum over the vector space dimensions in the nth ideal. You look for the monomials of degree j, count them, multiply by t to the j times s to the n. And then and this is a good exercise in definitions. This is the very same thing as the Hilbert series. This power series we just introduced, where we use this language L and this weight function. And our weight function ended up in a polynomial ring in two variables. So this is our form of power series in variables S and T as well. And this is rational. Notice this is almost the equivariant Hilbert series we defined, because what I wrote here is equal. Well, we computed yesterday what's the Hilbert series for the zero chain. So, and I denoted the zero chain by capital O. And then you have just to subtract the equivariant Hilbert series of the chain I as defined yesterday. So this is, so as a reminder, this is just the zero chain. We computed this and we set out, we wanted to compute this Hilbert series. So since we know this one, well, computing this one is equivalent to computing this formal power series. And so you can say, well, did we gain anything? And now the point is, yes, this is actually computable algorithmically. All right, so we'll have to do this. Oh, I should pause questions before proceeding. Let me check, is there anything? All right, well, okay, so then let's rephrase what do we want to do now? Or what did we do? We want to compute, we started out to compute this formal power series. And now we translated this problem into a problem of counting monomials in a formal language using a weight function. And then we had seen, well, this is basically equivalent to what we want to achieve. And so now we have to show we can do this counting. And for this, we need another concept, namely, let me recall what is a deterministic finite automaton. And this is, well, so deterministic, I will typically not even mention. So this is a finite automaton. On a finite set, our alphabet sigma, this is a 5-tuple. So bear with me. There are lots of words, but the idea is actually quite natural. So, okay, so we have 5 ingredients for an automaton. We have a set P. We have our alphabet sigma, a map delta, P0, and F. And now let me say what these are. So our automaton will have finitely many states. and P is our set of states. So the elements are the states. Sigma is our finite alphabet. Delta, well, let me come to delta last. When P0 is our initial state, where we always start. And then where are states where we can leave or accepting states. Okay. And then delta, this is the so-called transition map. Maybe I should say before this, I mean, these are lots of symbols. So what one can do and what you will do is you can always describe such an automaton by a cartoon. So let's do this sort of an example to illustrate this somehow. And let's do this with our alphabet where C is 1. So instead of zeta 1, I just write zeta. And let's consider an automaton just with 5 states. So we would start, and then so we start somewhere, and then we have states, say 5 states. So in this case, P has 5 elements. We'll start here. So with the state 1, which would be our initial state, P0. And then we have accepting states, and accepting states we encircle again. So this is, sorry, this went too far. So this is an accepting state, the only accepting state. Now, we need also a transition map. And this is a map where the domain will, from D into the set of states, where the domain D lives in a product of Cartesian product of P and sigma. So in other words, to each, what does it say? To a state and to a letter in the alphabet, we assign a new state. Okay, now we want to connect this to languages. And so before I complete this, let me say that this automaton accepts or recognizes a word W, and let's denote its letters by A1 up to, say, AS, and this is a word in the alphabet sigma. If there is a sequence of states R0, R1 up to RS, with the following properties. Well, the first state should be at the initial state, so that should be P0. And the last state has to be an accepting state so that we can actually end the word. So this is an accepting state, RS. And then the crucial thing is, how do we go from one state in the sequence to the next one? Well, state with index j plus 1 has to be the image of some state, the previous state R sub j, and some letter in our alphabet. And so we symbolically, we denote this by, we go from the state R sub j to the state R sub j plus 1 by concatenating what we have with the letter A sub j plus 1. So if I, and so these are my transitions. Delta are my transition up. Delta is encoded in these pictures. And so if I complete this, if I can go from state 1 to state 1 by appending tau, and then from 1 to 2 by appending sigma, from 2 to 3 again. Sorry, too slow, by appending another sigma theta. Here again another theta, and say from state 4 I go where by appending tau, but I can also go from 4 to 4 using theta or tau, and so on. Then I go from zeta, from state 2 to state 1 back using tau. Okay. Questions?
I have a question.
Yeah.
So this automaton in the example is not deterministic, right? Because delta is not a proper map, right?
Actually, it is. It's just, I mean, I can go from one, well, I mean,
But from 4 with tau, you can go to 4 and also to 5, right? So
yes, because I made my domain the tuples. Sigma.
Okay.
Right here, one is, the state is always 4, but the letter is different.
Yeah. Okay. Thank you.
Yeah. Thanks for asking it. This is good, because I mean, yes.
So can I also ask something on this? So deterministic means that D can be a subset of the set P times sigma. Otherwise, it's a regular automaton.
Exactly.
Okay, thanks.
Thank you. Okay, well, then, so let's check what words are accepted by this automaton. So how does this go? I mean, we have to start here. And once we are in state 1, we can go back to 1, adding a tau, or we can go back to state 2, adding a theta. And then we could go back to via tau and repeat. And this way, I mean, just going between state 1 and tau, you can produce any word where the letters consist just of zeta and tau. So if we start, the first parts, we can do anything with zeta and tau, and then we use this, all the words in zeta and tau, we denote by the star notation. But eventually, if you ever want to leave, you have to go to number 5. And then from state 2, there's only one way to go to 3. We have to add a zeta. And even though if you go to the last thing, if you arrive at state 2 and go to state 3, we must have already added a zeta. So if we are in state 4, in state 3, we must have had already 2 zetas to go from 3 to 4. We need another zeta. But once we are in 4, then we can again append any zeta or tau. So this looks again like any word in zeta and tau. And then to get to end, we have to add a tau. This is the language this automaton will accept. And that's probably a lot all at once, but I mean, I trust you, if you do this at home, you will see this. But I should ask if there are right away questions. Now, what's the connection to what we did previously? I claim, and again, I encourage you to check me on that as an exercise. This is the regular language to the sequence IN and at least one generated by the ideal I1, which just consists of is generated by the monomial x1 cubed. All right, so, and maybe the reminder is, or maybe that's, I mean, x1 cubed, sorry. That means we need 3 letters zeta for sure, and this is what this guarantees, this string. And this is in the first ring, so we need at least 1 tau, which we guaranteed here, and then you can multiply and do it. I mean, there are things to be checked, but as I said, I encourage you to do this. How is this related to regular languages?
Can I ask a question before?
Sure.
Going also in the chat, and
yeah.
it's important. So in stage 4, when you are there, you can go with a tau. You can go again to 4, or you can go to 5.
Yes.
So that means that there is a tuple for tau.
Oh, did I?
However, I can also add this, that deterministic and not deterministic, like you can go from one to the other. So
yeah, sorry, actually, oh.
In the definition here it is.
Thanks for checking. So let
Maria
me.
did that. So.
No. Let's make this better. That we have seen the pattern how we should produce this. Stop. I think that. Yeah, I think that's it.
Uwe, can I
Yeah,
also ask something? But
yeah, of
then,
course.
like, aren't you missing if you're in state 5?
Yeah.
I mean, so how do you get like this last part, this like theta tau star? So all words on theta tau. I mean, you said that if you're in state 4, you can basically produce any word of the form theta tau star.
Mhm.
But I mean, here from how you drawn the automaton, I guess, I mean, whenever you've read one tau, you have to read a theta or you are done. And so I don't see how you get like sequences of taus there. And the same applies to state 1, but there I don't see how you get like sequences just of thetas.
Oh, I should have allowed. Ah. Okay.
So I guess in the last state, you can
Yeah,
just
yeah.
have a loop, but
Okay. Okay. So let's go back to. Okay, I see. So let's go back even to here. It's the same question basically, right? And so you say if I go from here, I use a tau, but when I have a zeta, and then I have to use a tau. So how could I produce tau? How would I get, say, tau? Oh no.
so how would you get, let's say,
Yeah,
tau theta cube,
squared. Oh yeah.
yeah, squared tau, whatever.
Oh. Oh, and yes, and you're. Ah. Yeah. What did I? Oh yeah. Mm.
Oh.
Yeah. I need a zeta here. And then I can go back. And similarly here, I need a tau.
Okay, but now if you are in state 2, again, it's not deterministic.
Ah. Okay, so I shouldn't count.
Sorry.
No, it's good. Sorry, I apologize. I should have thought about this more.
You can also save yourself in general by using the empty word. Like if
Oh
you
yeah,
find a very silly, like, yeah.
I could use the empty. Oh yeah. Oh, that would.
And that's, or you can use a non-deterministic, which with less states and which is, I prefer
I
that
didn't want
one,
to.
but
Okay. Sorry. Yes, you're right. I mean, there is an empty. There is still the empty word, or I could use this. I didn't want to use it, but probably I should have here at least. It's true. That would save me. But then, no.
you would have one extra, 1, 2, 3, 4, 5, one extra state.
Let me, well, for now, I would need an epsilon, so for the empty corresponding to the empty word. And that's not completely satisfactory. You can always get rid of it, but I don't want to do it on the fly because I messed up already once. I have to think about this. But the point of this is the connection to regular languages. And that's the following a beautiful result, namely a formal language. Well, is regular if and only if it is recognized by a finite automaton. Okay, so and we have seen, we have already we always can associate to our ink invariant sequence a regular language. And now this tells us to a regular language, we can associate a finite automaton. And this is good because once we have a finite automaton, we can actually compute this formal power series defined using a weight function. So to do this, and this is actually a formula. So let me describe the formula. So given an automaton, finite automaton as above, with capital N states, oops, P, the set of states, P, capital P consists of states P0 up to Pn minus 1. We define a 0, 1 matrix M sub A for each letter A in the alphabet sigma by, well, we say, what is the index in position ij? And this is 1 if there is a transition delta from state P sub j via A to state Pi and 0 otherwise. So this matrix has size n by n. And so this is an n by n matrix. So in, say, k to the n, let's use E1 up to the n to denote canonical standard basis. So E1 is just the letter 1, 0, 0, 0 in k to the n, and then define a new vector U as the sum over the basis vectors EI in k to the n, where I varies about, the index I varies about the states P sub I minus 1 that are finite. So these are just all we did. We defined the matrix and these vectors, and then the connection is if V is a weight function on the alphabet sigma into the monomials in a polynomial ring in T1 up to Tk. Variables the weight function. And L is the language accepted by A. Then we can compute this desired formal power series as follows. We take the vector u we just defined, its transpose, we multiply it by a matrix and then multiply by E1. And what is the matrix? We take the identity matrix and by any identity matrix minus the sum over letters in the alphabet sigma, where we evaluate each letter at using V multiply by the matrix M sub A. That's an n by n matrix. And then we take the inverse. And that we multiply by E1. Okay. Now, actually, if you think about proving this is pretty straightforward. You can also find this in Stanley's book, for example. But what's the beauty of this? Once you have the automaton, well, this gives you the recipe how to compute these matrices, and then you just have to compute this inverse matrix. But of course, that's just linear algebra. So that is then actually very fast. And that gives you a formula. So let me summarize the steps we have taken. So we want to compute the equivariant Hilbert series to some ink invariant chain. And so what we have to do, we saw first, we have to determine a regular language. L to I such that with, the sub-language where the count the number of occurrences of the letter tau corresponds to the monomials in the ideal I. So these should be all bijections. Then you have to find an automaton that recognizes L. And finally, you just have to evaluate this formula we just discussed. Yeah. And so this is in this. This is an algorithm that can do, and it's actually software help to produce it. I saw yesterday that I think Martina provided also an algorithm how to compute ink invariant chains using Macaulay. So that you can really experiment using this procedure. Sorry, this was the first part was a bit too long. Let me stop for questions. Okay. All right. Okay. Should have moved that. So now let's switch gears and let's come back to a topic Martina started, namely discussing simplicial complexes. But let's do this now. Let me call this up to symmetry. So simplicial complexes up to symmetry. All right. So in the first lecture, Martina described, if you start with a simplicial complex, delta on M letters, it corresponds to the Stanley-Reisner ideal I sub delta in a polynomial ring in M variables. And that's in the case C equals, where C equals 1. But that doesn't matter too much. Sorry. Much better. And so this is a square-free monomial idea. And now what we have discussed, we can take any ideal and it generates an invariant filtration. And if it happened that the Stanley-Reisner ideal was invariant under permutations on M letters, we could also generate a sim-invariant filtration. And what that meant, what did we mean by this generation of a sequence? The nth ideal would be just obtained from the m's ideal by applying increasing maps to the monomials in I sub m, strictly increasing maps that map the number integer m to an integer which is at most n. But if you start with a square-free monomial ideal, this will be again a square-free monomial ideal. So it will correspond to a simplicial complex. So what this means, starting with any simplicial complex, we can generate a whole sequence of simplicial complexes. And as discussed in some cases previously. You can
Sorry,
ask,
Uwe?
yes.
Is IM the same as I delta?
Yes, but I should have written I delta. This would have been better. Thank you, Alessia.
Thanks.
And so, but then we have a sequence of simplicity complexes, and I mean by this, the way we produce the corresponding ideals, they all look similar. So we can hope, well, how similar do the simplicity complexes look like? Or a little bit more precisely, can we say something about properties of the not simplices, simplicity complexes delta n if n is sufficiently large. Again, is there some stabilization of properties? So if we are far enough out in the sequence, can we predict what happens afterwards? And so some questions we could consider, for example, what about the number of facets of the simplicity complex delta n as n increases? What can we say about properties such as pureness? So what means pure? All facets have the same dimension. Or Martina introduced combinatoriness. So can we guarantee that for some n, all these will be combinatorial? And you can make consider other properties you may like if you prefer, instead of combinatorialness, something more combinatorial like shareability as well. When always shareable, vertex decomposable. You can ask your favorite question and consider it. But let's recall some things we do know. Or maybe before I recall what we do know, let me stop. Questions so far?
Sorry, can I ask one?
Yeah.
So, I mean, both in Martina's lecture and in your lecture, you're basically saying that a simplicity complex corresponds to the standard Reisner ideal. But I guess that, I mean, if you know how many vertices or how many variables you're using, that's true. But if you don't know that, and since we have these like indices, like in this case, we have the index going up, you might have a certain amount of cone points playing a role. So I'm kind of wondering whether you couldn't do that infinitely many times, but maybe for just going from one step to the other, you could try to see how the coned complex deforms when you go to the next step or something like that. Does it even make sense? I don't know.
You're right. I mean, you have to match the number of variables and vertices. But here I tried to be careful. This m has to be the same m here. And so in general, right, this would be, if I do this in general now, this would be in kx cn. And so that would be a simplicity complex on a vertex set with Cn points.
Yeah, sorry. No, but what I meant is that in the, like, you could say that delta n, you could see that as a complex on C times n+1 vertices, but like, C of them are cone points, and then you could just see what happened to the, like, from going to from step n to step n+1. That's what I was trying to say.
Oh, yes, but I insist on this recipe.
Okay.
Yeah. Yeah, I mean, so what you are saying is if I would only allow the identity map, then I would take cone points over and over again. That's not so. Anyway, this is what we had seen. If we have any invariant chain, you can always find an ideal in the chain such from then on everything is obtained by applying these maps. And so I use this as my recipe for producing a chain, and so for the corresponding simplicial complexes. We'll look at examples very soon. Yeah. Well, I mean, we could yeah, let's hold off a little bit. Let me recall what we do know. We know already that the dimension of these simplicial complexes becomes a linear function in N eventually. And the degree of these ideals becomes an exponential function. And now how is this related to our simplicial complexes? The degree is simply the number of facets of the complex with maximal dimension. So in other words, the dimension is equal to the dimension of the simplicial complex. Or you could think of this intuitively as the volume of this complex. Now, to describe examples, it's helpful to recall the following fact. So if you have a simplicial complex, and now let me go back to N letters. When Martina pointed out that it can be described, or it's determined once you know the facets. And so since we have a bijection between simplicial complexes and square-free monomial ideals, there should be an algebraic interpretation of this, and this is what I would like to describe. So if you take any face element of our simplicial complex F, let's denote by M sub F bar, the ideal generated by the variables that have an index which is in the complement of F. So this F bar is meant to indicate the complement of F. And then it's not too difficult to show that the ideal of the simplicial complex delta is the intersection over all faces in delta of these ideals just introduced. And now, if one face is contained in the other, the complement of the smaller face just has more variables. So this would be an ideal that is redundant in this decomposition. So if we avoid redundancy, we can just write this as the intersection over all facets of delta and then take these corresponding ideals. And so this is, and that becomes unique. So this is a unique decomposition of the Stanley-Reisner of the ideal of delta as intersection of ideals generated by variables. So maybe to illustrate, we're still in a finite setting. So let me use a simplicity, almost the complex that Martina used. Oops. And so let's say this is 1, I think 2, well, doesn't matter. 1, 2, 3, 4, 5. And I want these triangles to belong to it. And so when we had seen the Stanley Reisner ideal to this complex is determined by the non-faces. And well, we'll see, of course, 2, 5 are not connected. And so 3, 4 and 3, 5 are not connected. So these have to be in the, I mean, the corresponding monomials have to be in the ideal. So we need x2, x5, x3, x4, x3, x5. But we are missing also the triangle or the simplex with vertices 1, 2, 4. So that is another monomial in the ideal. And that's the Stanley-Reisner ideal. Alternatively, what we just discussed, we could look at what are the facets. Well, the facets 1, 2, 3. Then we have 1, 4, 5. And we have 2, 4. And now I was too wasteful with time. Now I want to define these ideas, right? I take the complementary indices, and that gives me the corresponding ideals. So I claim 1, 2, 3, the complement is 4 and 5. So I take x4, x5. Complement of 1, 4, 5 is 2 and 3. And 2 and 4 has as complement 1, 3, and 5. Okay. And now, well, I better pause. Questions for the example or other questions? So now let's do this up to symmetry. So now, and let's, instead of ink invariant, let's just take sim invariant chains. Well, say of square-free monomial ideals or equivalently simplicial complexes. Okay. So what we want is, so we want each ideal I sub n, which is the polynomial ring actually in C times n variables, C rows and n columns. We want this to be sim invariant. Sim n invariant. Okay. And now let's start with the easiest case, C equals 1. And then if you look at the monomials of degree k, there's only one square-free monomial up to symmetry. Yeah. Namely, there's only one square from a monomial of degree k up to symmetry, namely the product of x1, x2 up to xk. And any other one you get by applying a permutation. So if you want to have a symmetric ideal generated by these monomials, you basically have only the orbits corresponding to such an monomial. So we only have to study the sim orbit of such a monomial x1, x2 up to xk, where k is at least 2 and fixed. Oh, yeah. So in other words, what is our ideal IN? It's just obtained from this monomial by applying permutation of n letters on this monomial. So that corresponds to a simplicial complex. And let me describe it algebraically, and I encourage you to work this out as an exercise. That's the intersection over all ideals xi1, xi2, xi with index n minus k plus 1. So Each such ideal is generated by n minus k plus 1 variables. And the condition is I1 is at least 1 less than I2 less than I3 less than I sub n minus k plus 1. And this last index is at most n. Okay. So what we see, we can take, I could have said with other words, you can take any subset of n minus k plus 1 variables, take the corresponding ideal, and then take the intersection over all these ideals. That will give you the ideal, the nth ideal in this sequence. So by the recipe above, the facets of the corresponding simplicial complex are just the complements, but the variable, I mean, the idea, these ideals are generated by n minus k plus 1 subsets. So the facets correspond to k minus 1 subsets. So these are just k minus 1 subsets of the set from 1 to n. In other words, we see that this simplicial complex is just a k minus 1 dimensional skeleton of an n minus 1 simplex. The dimension is k minus 2. Each facet has k minus 1 vertices. What's the degree? We said the degree is the number of facets of maximal dimension. All facets have the same dimension, so we just count them and we see that's just a binomial coefficient and choose k minus 1. All facets have the same dimension, so that's the same as saying delta n is pure. And then one takes more work to show, but all these complexes are also Canonical. So for a particular example, if you take k equals 3, then the complexes have dimension 1, and in fact, delta n is just a complete graph. On n vertices. So, I mean, so if you have just one row of variables, that's and we insist on symmetry, that's the whole picture. So let's make it more interesting. Let's consider c equals 2. So we have 2 rows of variables, and to simplify my notation, let me denote the variables in row 1 by x1, x2, but the variables in row 2 by y1, y2, and so on. Okay. And now let me make my life easier. How many monomials are there up to symmetry of degree 2? So I want to just look at monomials of degree 2 up to symmetry. Well, I mean, we have seen a recipe before. X1, X2 is certainly 1. Analogously, y1, y2. Are there others? Oh. Should have opened the chat.
X1, Y1, for example.
Yeah, x1, y1. Is that all?
Antonio is saying x1, y2 also.
Yeah, x1, y2. But that's it.
But we need to square polynomials.
Oh yeah, yes. Right. Yes. From now on, everything. Oh, this is all square free. Yes, thank you. Okay, so let's consider these one by one. So let's consider their orbits. As in the case above. So if you look for the orbit of x1 and x2, or the orbit of y1 and y2, well, that we have already looked at. This is as in the case we just studied, right? If k is 2, that we already did this. So let's move on. Let's look to the next monomial, x1, y1. So sorry. Let's look at the orbit of x1, y1. And what is then the nth ideal in the sequence? It's just the ideal generated by x1, y1. I mean, we have only the image of one, so it's just another product xi, yi. So it's just the nth ideal is generated by n monomials x1, y1 up to xn, yn. And this is actually an idea where I described the Hilbert series already yesterday, because you could think of it, this is obtained from I1. It's just in the polynomial ring where all row where you have only the first column of variables. And so we get that the Hilbert series is just 1 plus t to the power n over 1 minus t to the power n. So that already tells us that the corresponding simplicity complex has to have dimension n minus 1. And the h vector corresponds to the numerator polynomial, which we, of course, we wrote down. So the h vector is just given by hi is n choose I. And by what Martina described, we could compute from this, of course, the complete phase vector. Moreover, I had said, well, what is the degree? You evaluate the numerator at t equals 1, so it has to be 2 to the n. So we have 2 to the n facets, and now I claim I can write the ideal as an intersection of ideals generated by variables A1 up to AN, where the i's generator AI is either xi or yi. And so for each I, we have two choices, which gives me 2 to n facets. And in fact, these are, so the facets are the complements, and they have a similar description. They all have the same dimension. So this is pure. And one can also show again and Complementary. Let me pause for questions. And again, I mean, I give you these results, but I encourage you to check these. I mean, this is, you can do this by hand. So now we have looked at the orbits of the first 3 monomials, one more to go. Let's take this one. So let's look at now the orbit of x1, y2. So the nth ideal, we just apply any permutation to xi, y2. So the generators are all monomials of the form xi, yj, where I is not j. These are both indices in the set from 1 to n. That's the idea. Equivalently, I can write this as an intersection of ideals generated by variables. And again, I encourage you to check that this is the same as the intersection generated by the variables x1 up to xn. The ideal generated by the variables y1 up to yn. And then you take the intersection with all variables, ideals generated by variables. Maybe I say it in words. You have to choose n-1, all but one of the indices, and then for each index, both variables. So it's xi1, yi1, and so on, up to xi n-1, yi n-1, where I1 is less than I2, up to I sub n-1 is at most n. So this gives us the description also of the facets. So we see the complement of the, well, to the ideal, well, the facet corresponding to the ideal x1 up to xn, plus the vertices y1, yn to y1, yn. We have x1, xn, then we have y1, yn. And here we said we leave out just one index and then both the variables. So this is xi, yi, where with I any integer between 1 and n. So this time we see, well, these two facets have both dimension n-1. These facets have dimension 1, But overall, this means that the simplicial complex has dimension n-1, but it is not pure. And then it's a general fact, if it's not pure, it cannot be Combinatorial. What's the degree? It's the number of facets of maximal dimension, but we have always 2 of these only if n is at least 3. So maybe to illustrate what these complexes look like, if n is 2, we have the simplex to x1 and x2, the simplex to y1 and y2, but then we have also x1, y1, and x2, y2. If n is 3, again, we have the simplex to x1, x2, x3. Sorry. Then there is the simplex to y1, y2, y3. And then we can, when we have edges between any 2 variables with the same index, so we get an edge between y1 and y2, x3 and y3, and 1 between x1 and y1, and that's it. And so if you want to complete this, if you insist that all your generators in the square monomial ideals have degree 2, so now we considered the orbits of each of these individual monomials. Now you could consider sums of orbits. But this is again a finite number, and I encourage you to work with art. And actually, there are sometimes surprises. The sum of 2 orbits could look simpler than the individual orbits. I encourage you to check this. So it's not that this gets always more complicated. But let me stop here and invite questions.